So welcome to this lecture. In today's lecture, we will learn restoring division and non-restoring division algorithm with respect to a particular problem statement. So the problem statement given to us is in a small town, there are three temples in a row and a well in front of each temple. A pilgrim came to the town with certain number of flowers. Before entering the first temple, he washed all the flowers he had with the water of well. To his surprise, flowers doubled. So he offered a few flowers to God in the first temple and moved to the second temple. Here also, before entering the temple, he washed the remaining flowers with the water of well, and again his flowers doubled. He offered a few flowers to the God in the second temple and moved to the third temple. Here also his flowers doubled after washing them in the well water. He offered a few flowers to the God in the third temple. There were no flowers when the pilgrim came out of the third temple, and he offered same number of flowers to the God in all the three temples. So what is the minimum number of flowers the pilgrim had initially, that is x, and find the value of x divided by 3 using restoring division method. How many flowers did he offer to each god, that is y, and find the value of y divided by 3 using non-restoring division method. So this is the trivial question to us. So first of all, we need to find the value of x and y. So with the problem statement given to us. So a pilgrim, as before entering to each temple, the flowers is doubled. So when he washed the corresponding flowers what he had in his hand in the well, and subsequently he has offered some flowers to the god in each temple, and the condition given is for each temple he has offered the same number of flowers. Okay, so we need to start from the first temple. So let we consider that x number of flowers he had before he entered the first temple, right? So when he washed the flowers what he had in the well, so it has doubled. So it becomes 2x, right? So in that 2x of flowers, yes, let me consider that he had offered y flowers to the god. So after coming out of the first temple, he had 2x minus y flowers in his hand. So what happened when he entered into the second temple? Now when he entered into the second temple, same thing he has done, he has washed the flowers. So it has doubled. So 2x minus y into 2. So it becomes 4x minus 2y, right? So he has offered the same number of flowers to the god. So we need to subtract y. So 4x minus 2y minus y. So it becomes 4x minus 3y. So after he has given some y flowers to the second temple, okay, same number of flowers as he had done in the first temple. Now it becomes 4x minus 3y after we come out of the second temple. Now what happened to the third, when he entered into the third temple, again the flowers doubled when he washed the well. So 4x minus 3y into 2. So it becomes 8x minus 6y. And he have offered the same y number of flowers. So it becomes 8x minus 7y. So after he came out of the temple, third temple, so he had 8x minus 7y. And subsequently, what is the statement given in the problem is, after he came out of the third temple, okay, he does not have any flowers. So that is the problem statement given to us. So 8x minus 7y is equal to 0. So that is the equation for us. Now if you substitute the minimum value of x as 7 and y as 8, then the minimum value of x is equal to 7 and y equal to 8. Okay, so this condition will be satisfied. So 8x minus 7y is equal to 0. Okay, 7, that is 7 into 8 into 7 is 56. Similarly, 7 into 8 is 56, right? So the minimum condition is satisfied here, right? So x is equal to 7 and y is equal to 8. Now we have found out the value of x and y. Now we are in a position, okay, to divide, okay, to perform the division, x divided by 3 and y divided by 3 as asked in the problem. Okay, So 7 divided by 3 we need to find, and 8 divided by 3. 7 divided by 3 using restoring division, and 8 divided by 3 using non-restoring division algorithm. So 7 is to the base 10. Okay, when you convert it into binary, it is 0 triple 1, so it is dividend. Okay, 3 to the base 10. When you convert it into binary, it is 0011, which is a divisor. Okay, now we will move on to the first division, restoring division of 7 divided by 3. So before going to this problem, we will have that algorithm. Okay, in our we need to have the algorithm in our mind, so that before starting the solution to the problem. So if you see, we are going to initialize these values. The A register to 0, M is going to hold the divisor, Q quotient is going to hold the dividend, and we are going to have the count. Okay, so number of bits, so a number of bits. The first step is we are going to shift left the A and Q registers and perform A is equal to A minus M. When performing A is equal to A minus M, if A is less than 0, that is negative, okay, then if it is negative, then we are going to assign the Q0 value to 0, and again we are going to restore the division, that is A is equal to A plus 1. So this is the step where we are going to perform the restoring, okay, restoring of A. So that is the A is equal to A minus 1 is true, that is it is negative, okay, then we are going to restore the value of A. So if it is not, okay, so A equal to A minus 1 is not negative, then we are going to assign Q0, okay, that is LSB of quotient register to 1, and then we are going to proceed to decrement the count. So in this way we need to perform these step iterations till the count reaches to 0. So this is the algorithm for restoring division. Now we will come to the problem. So the restoring division 7 divided by 3. So we have converted the 7 into binary and 3 also into binary. Okay. We know that M is going to hold the divisor. Okay. So 0011, and because we are going to perform A is equal to A minus 1, minus M. So we are taking the 2's complement of M also for that particular step. So if you get the 2's complement of M, it will be minus M. So it is 1101. So that is 2's complement of 0011, right? So your A register is 0, all 4 bits, and Q quotient register is assigned to the dividend 0111. Okay. So now this is going to be the A register, and this is the Q, right? So for the first iteration, so we do not know the corresponding Q0 value. Okay, Q0 value, we are left shift. We are going to left shift the AQ. So this is A, this is Q. So when you are going to left shift, okay, this 0 comes here, this 0 comes here, this 0 comes here, and the 0 which is available in Q, okay, that is comes here, and the remaining 1, 1, 1. Now the last bit, that is LSB bit of AQ. Now we are not, we need to determine that. So how to determine? It is depends on the value of A equal to A minus M. Okay. So A equal to A minus M. So already we have calculated minus M. It is 1101. So we are going to add these two. So it is less than, that is MSB is 1. So it shows that A is less than 0. So if it is A is less than 0, what we are going to do? We are going to assign Q0 to 0. Right? And what happened? If A is less than 0, what we need to do? We need to restore the A register. So again we need to perform A is equal to A plus M. So when you perform A is equal to A plus M, then you will be restoring to the original value 0011. We need to add it with the 1101, so that to retain the original value 0000, as was the case in the start of the first iteration. So now we have got the restored value, right? Now we will move on to the second iteration. So the count will be decremented to 1, right? Initially count was 4, okay, because n bits divisor, okay, 4 bits. So in our case it is 4 bits. So again left shift AQ. So this 0, this 0, this 0. So the MSB 0 will be going out of the register, right? So this 1 comes here, this one comes here, this one comes here, and 0 comes here. Again, still we do not know about the last LSB bit. So for that we need to perform A equal to A minus M. So A equal to A minus M. Minus M already we have, so we are going to add 1101 with this, and we are getting again MSB as 1. If MSB is 1, then it is a is less than 0. If a is less than 0, assign q naught to 0. So we have assigned q naught to 0. Right, and then because it is negative, again we need to perform the restoring a equal to a plus m. So we need to add 0011 with the existing value of a, which is 1110. So to retain the original value, okay, during the start of the iteration. Now if you see, after adding, so we are getting 0001, which was the case which when we have started this iteration. So we have restored the value. Now we move on to the third iteration. Again, after the second iteration, the count bit will be reduced to 1. So now it is 2. Now the left shift AQ. So left shift, this 0 goes out of the register, 0, 0, this 1 and this 1. This one comes here, this 0, this 0. Now we do not know the LSB of Q naught, that is we do not know the value of Q naught. We need to perform A equal to A minus M. So when you perform A equal to A minus 1, it becomes 0, 0, 0, 0. All is 0, 0. So it is A greater than 0. Okay, if A greater than 0, assign Q naught to 1. Right, so if it is a positive value, we are not going to restore the value of the that is A register. Now we can move to the next iteration, fourth iteration. So here if you see, again the count is decremented, so it becomes 1 now. So the left shift AQ again we have performed. So these 3 zeros will come here, this 1 will come here, and 001 will take this place, and still we do not know the Q naught register. What is Q naught value? So A equal to A minus N in perform, then it becomes again MSP is 1. So it is A is less than 0. Because A is less than 0, we are going to assign Q naught to 0. Again we need to restore the corresponding A register. So by adding A equal to A plus 1, if you perform A equal to A plus 1, this is becomes 0001 and your quotient is 0010. Now after dividing, what is the original division? 7 divided by 3 for us. 7 divided by 3 means your quotient register should be 2. Okay, 7 divided by 3, quotient register 2 and the remainder register is 1. Okay, so this is the result for restoring division. Now we will go for the non-restoring division. So because y value is 8, we need to perform 8 divided by 3. Okay, so for our understanding, again we will take up an example flow chart for non-restoring division. So in the non-restoring division, we are going to initialize with A value, A register 0, M is divisor, 2 is dividend and count is n. Okay, now if you see the case, if A is less than 0, okay, if A is less than 0, if it is true, then we are going to shift left AQ and add A equal to A plus m. If A is positive, we are going to perform shift left AQ and A equal to A minus m. Okay. So after this step, if still A is less than 0, what will happen? If it is true, then we will assign Q naught to 0. If it is no, we are going to assign Q naught to 1. And we are going to decrement the count. If the count is equal to 0, we are going to end the division process. If the count is not 0, we are going to iterate it. Okay, so the two-step process is here. Okay, so now we will move on to the problem. So M value is 0011, that is assigned here, that is divisor 3, and the A register is assigned 0, initialized to 0, and Q register to 8. 8 binary is converted into binary, it is 1000. Now what we need to perform, the first step, left shift AQ. So we are performing the left shift AQ. So if it left shift, it becomes 0001 and 000. We do not know the value of this Q naught register. Okay. So what we need to do? So we need to perform A is equal to A minus M. So minus M we need to calculate. Already we have calculated for the first problem. So same thing we are going. It is 1101. We are going to add it. And if it is A is less than 0, so it is what we are going to do. We are going to assign Q naught to 0. So we have assigned Q naught to 0. Okay. Now what we need to do? Left shift AQ again. Okay. We are not restoring it here. Left shift again AQ. Okay. So when you shift it, this one goes out of the register. This one comes here, this one comes here, then 0 comes here, then this 0 of Q register comes here. Okay, then these 3 zeros takes this place. We do not know the value of Q naught. We are going to perform A equal to A plus M. Why A equal to A plus 1? Because it was previously negative. Okay, now 0011. So we are going to add it, and if it is still A is less than 0, we are going to assign Q naught to 0. Then again left shift AQ. So if you shift left a q, again we do not know the q naught value. Now we are going to perform a equal to a plus 1 because previous step a value was negative. Okay. Now what after performing a equal to a plus m, then it is a greater than 0. If a greater than 0, assign q naught to 1. So we have assigned q naught to 1. So left shift a q. Okay, it's left shift a q. Again it becomes 0, 0, 1, 0, and we do not know the q naught value. Okay. Now we perform a equal to a minus m. Okay, right? A equal to a minus m because the previous value of a is positive. Okay, so that is a equal to a minus m. So it results in double one double one. So if it is a is less than 0, so if a is less than 0, assign q naught to 0. We have assigned, and finally we need to perform a equal to a plus m. So a equal to a plus 1 gives 0, 0, 1, 0, and which is available in the A register, and the quotient register 0, 0, 1, 0, which is the final result. In each iteration the count value is decremented. So here it is count equal to 3, 2, 1, 0, right? So we have stopped the iteration, and finally if you see here, M register also holds 2 and Q register also holds 2. Okay, right. 8 divided by 3, right? Remainder is also 2, quotient is also 2, right? So this is the solution to the problem.